So this is the start of chapter 9 notes, and it's just a continuation of what we've been talking about in chapter 8. So I put both of these together. While we go through this section, you might want to print out my VSEPR table that I have for you. Take that out while we go through these shapes. So there are different theories of how these molecules organize themselves in three-dimensional space, and one is called VSEPR, valence shell electron pair repulsion. Another one is called hybrid orbitals, which I will talk about, and a third one is called molecular orbital theory. So these are all found in chapter 9. So when we first taught you this back first year, we really looked at what we call the electron group shape. Was really the shape that we were giving you to kind of know or memorize. There's far more shapes than we covered first year. So this is how we believe the molecule to exist three-dimensionally, okay? And so we are always focused on what we call the central atom in terms of how many bonds does it have, how many lone pairs does it have. So there's going to be a notation we're going to use. It's called AX. A stands for the central atom. There's going to be a number down here for X and a number down here for E. X is going to be the number of bonding pairs around that central atom. And E is going to be the number of lone pairs around the central atom only. So it's not all lone pairs, it is just around the central atom. So it's called AX. So you're going to see me use it. You see some books talk about it. And you are going to have to know what we call the molecular shape. So molecular shape is only including the bonding pairs. So you're going to see kind of both of them. So I'm going to say electron shape versus molecular shape. I'm going to have the notation, the AX notation, then give you an example. And again, there are other examples on this sheet as well. I try to come up with as many as possible. So I'm going to start with the linear shape, and I'm going to keep adding to it. So first off, electron shape is linear, molecular shape is linear. So the notation we are going to be using is the X is a 2, so there's 2 bonds and no lone pairs around that central atom. So beryllium is one of those that can make a linear shape because it can only make 2 bonds. And if you draw it out, you will see that it has a degree of 180 because again, that's the distance, what we call the bond angle. It is the distance between this bond and this bond. So next shape that we have is something called a trigonal planar. Trigonal planar is AX3E0. And again, you're going to see that sometimes E is not included if there is no lone pair. So boron is a great example. Boron only makes 3 bonds. And so this one is actually in 2 dimensions, is the same as it is in 3 dimensions, meaning it is flat. So you have boron and then you have 3 bonds going out from it at about 120-degree angles. That's what we call a trigonal planar. Trigonal planar, but the molecular shape is now different. Okay, so this is bent or angular. So if you have a lone pair, so it's AX2E1, if you have a lone pair on that central atom, and you have bonds going away from it, 2 bonds, and again, this has a double bond. That does not mean there's still just 2 different, what we call locations for bonds to form. So that's why it's still a 2. Really what you focus on here is if you're looking at just the molecule and you don't see the lone pair, you are just looking at the bonds. That is why it's called bent or angular. The degree measurement here is very different though, because it's 120. If you remember back to bent when we first taught it to you, it is different, and we'll talk about that. So this is the example is SO2. Now we get into the major shape, and this shape is called a tetrahedral. This is found a lot in nature. So it has 4 bonds and no lone pairs around that central atom. So the example I drew here is SO4 2-. This bond angle, again, in 3 dimensions, the oxygens can come further out. When you draw it on a 2-dimensional space, it looks like the bond angle is 90, but in actuality, it's 109.5. And again, this is all found on your sheet as well. Okay, it's all found on your sheet as well. All right, so the next one is where I'm going to have to add a couple things to your sheet. So this is called a tetrahedral trigonal pyramidal. So trigonal pyramidal is AX3E1. So this is if you have a lone pair on that central atom and then you have 3 bonds going out from it. So SO3 2- is an example of this. Now the bond angle between the oxygen and oxygen here, and again we're talking bond angles, not the lone pairs, is influenced by that lone pair. The lone pair is pushing those bonds away. So it really starts out as a tetrahedral, meaning that lone pair takes one of the areas where you would have a bond. But because the lone pair doesn't like the bonding pair, you get a smaller bond angle. So that's the one thing I don't like about this sheet, is they don't really account for that. So if you would go to where it says tetrahedral, AX3E trigonal pyramidal, and cross out the 109.5 and change that to 107. It's actually 107.3, but if you remember 107, that's going to be good enough for me. And I will show you how you easily memorize that. All right, and the last one with the tetrahedral is our classic bent that we taught you first year, which is our water molecule. Okay, so the bond angle here is about 104.5. It's we'll just call it 105. It's when you have 2 bonds and 2 lone pairs around that central atom. So it's called bent or angular. Again, because you now have 2 lone pairs pushing away those bonds, that bond angle is smaller. So if you want to change the next one on your sheet, you could change it to 105, or sometimes you will see it as 104.5. As long as you know that you are essentially getting a smaller bond angle each time you add some lone pairs. And do realize the lone pairs are these little bubble things on your diagram. All right, so then we go to a place called beyond the octet. Okay, so this is where we're going to have more than 4 bonds around a central atom. So this is called a trigonal bipyramidal, and we've not seen this first year. So this is AX5E0. So I'm going to put the central atom and then 5 bonds around it. Now, it's space-wise, what it is really a triangle. So if you draw a triangle and put an atom on each end of the triangle, and then have something above the plane and below the plane, that is really what a trigonal bipyramidal is. Think of a triangle, trigonal. Bipyramidal means a pyramid above and below the plane. So we have a couple different bond angles here because of the fact that you have a couple different things. So on the triangle itself, it's a 120. Above and below the plane would be the 180, and then from the triangle to one of the bonds above or below the plane would be 90. So that's why you will see on your table that it has all 3 of those listed there for it. And I do like this picture. It does a very nice job of showing you that versus what it would look like stick-wise. All right, then we could go into some more fun ones, okay? This is called trigonal bipyramidal, but it's a seesaw. So when I start to get a lone pair on that central atom, what it's going to make is literally a seesaw. So if you think of a seesaw in the park, it goes back and forth. It could vary between those 2. So all I want you to do is to draw a lone pair and then 4 chlorines around, and you will never have to draw it according to what the actual bond angles are or anything like that. I just want you to have the right number of lines, right number of lone pairs, so on and so forth. So that's called a seesaw. So it still has the 90, the 120, the 180 as a traditional trigonal bipyramidal. So the next one is called trigonal bipyramidal, but it's called a T-shape. So it's literally what you think it will be, meaning you're going to have a T-shape for the bonds, and then you're going to have 2 lone pairs on either side of that central atom. So it's hard to draw it very nicely. If you go to your sheet here, they do a very nice job of showing you where those lone pairs are. It happens to be on the triangle part of it. So this is what it would look like stick-wise for you to kind of keep track of. And because of that, the T-shape only has a 90 and 180 because you don't have something else on the triangle anymore. So you don't have that 120 bond angle. You don't have that 120 bond angle. All right, trigonal bipyramidal can also be what we call a linear shape. And that is because you could have 2 bonds and 3 lone pairs, and those lone pairs are going to go on the triangle. And always keep that in mind. And the book does talk about why those lone pairs want to be there. It seems to be a much further space for them to go rather than to go above or below the plane. So that is why this is a linear shape. 180 is the only degree here. But again, it's when you have 3 lone pairs on that central atom. The last shape that goes beyond the octet is called an octahedral. Okay, so this is 6 bonds. So what you have is essentially a square or rectangle, and then you have something above and something below the plane. So the only bond angle you have for an octahedral is 90. So if you think of octa meaning 8, if you do kind of like a diagram, you know, if you were to connect the top part to here, you would actually make 4 different triangles on the top and 4 different triangles on the bottom. The diagram you have there kind of shows you a pretty nice picture of that. So that's why it's called an octahedral, because of that. Now, it does say 90 and 180, because again, if you're looking at above and below the plane, that would be what you see. Octahedral, there's 2 other ones. Octahedral as a square pyramidal. So if you have 1 lone pair on that central atom, so it's an E1, but you have 5 bonds. You have 5 bonds around that central atom. That lone pair is going to go above or below the plane. So it's called a square pyramidal. And for this one, being a square pyramidal, the only bond angle you could possibly have is 90. So that is where the 180 kind of drops off, is when you start to take off a bond from an octahedral. And the last one, I ran out of space, hopefully you still have space on your sheet, is a square planar. Okay, so this would be if I have 4 bonds and 2 lone pairs. So I have 4 things going out, and then I have a lone pair above and below the plane. So this is 90 degrees. So again, what this is trying to show you is the fact that the lone pairs in this case, the furthest away they could possibly be is above and below the plane. So different from a trigonal bipyramidal. So when I ask you to draw them, I do expect you to give me the electron shape and the molecular shape and keep those straight as to which way they go. I don't care how you draw them, just as long as you have the correct number of lines and lone pairs.